So this is your drain current and this is your load voltage. The value here should be 5 kilo ohm. So you just click on it here. Okay, so 5 kilo ohm. Now let us start the experiments. So this is my gate voltage. Right now I'm biasing them at the same voltage, but remember this is a potential divider network. So even if there's 20 here, right now my knob here is at minimum. So at minimum, which means that this is the arrow. So right now I am bypassing all of my potentiometer resistance. So all of the voltage here will appear here instead. So in a way, right now my gate voltage is 0 volt. So let's just have a look. For this statement, I'm using another type of MOSFET. They have maximum gate voltage values that you must not exceed, as well as the gate threshold voltage. This is an N-channel MOSFET from the online simulator, which is Circuits.io. Nonetheless, we can still proceed with the experiment. Just remember that if you have specific types of MOSFET, you can check the datasheet. For example, this type of MOSFET, the maximum gate to source voltage is 20 volt, and this is the minimum according to the manufacturer, the minimum gate threshold voltage that you require to turn your transistor on. Now my potentiometer is already at minimum, my gate voltage is equal to 0. Now already at minimum resistance, turn on the supply unit and increase it to 6 volts. Okay, now you're at 6 volt. This doesn't matter because this is my gate voltage. Now this is according to the type of MOSFET, which is the RF530 NPBF series, which is it requires at least 2 volt to turn the transistor on. For this, we shall have a look. I'm not sure its gate to source threshold voltage. So we shall steadily and slowly increase the gate terminal in steps of 1 volt until VG is equal to V1. So right now at 0, yeah, 10 millivolt is practically 0. Okay, so 10 millivolt is practically 0. Okay, so what is your drain current? Yeah, 0 as well. So you can draw the transconductance curve or the drain characteristic like this in a way. So this is your ID, this is your ID, and this is your gate voltage. So here at 0 you have 0 current, so VG is equal to 0. Let me put it nicely here. So this is at VG is equal to 0. So now let us increase this in steps of 1 volt. Hello, 1 volt. Okay, 2 volt. Yeah, this is about 2 volt. So still 0. So this is still 0. 1.83. Okay, let us be a bit precise here. So what does this mean? This means that the transistor is still not on. So if it's not on, it means that all of this voltage, which is now 6, I modified this to 6 according to the experiment. Okay, so this is 6. So here should be 6. So if I put my multimeter here, I should get 6 volt. So this is 6 volts. So it means that the transistor is off. You can see here your drain current is 0 amp. So let us increase this to 3 volts or 2.5 or whatever. Okay, let us take 3 point something. Okay, seems that at 3.34 now my transistor turns on, but not fully. Remember, it's not fully on yet, because if this is fully on, all of this supply voltage will be here. Okay, right now only some of it is here. So 3.34, my drain current is 23.7 milliamp. Okay, do you understand? So if you want to draw it like this, so at 3.3, so this is, for example, 23.7 milliamp. is equal to 3.34. Okay, if we keep on increasing our VG until it is equal to our supply voltage here, which is 6. So let us keep on increasing this to 6. Okay, this is close enough. 5.72. Yeah, close to 6. So 5.72, you get around 70.1 milliamp. At VG is equal to V1, VL is only half. So what does that mean? It is not, your transistor is not fully on yet. Okay, so how can we turn it on fully? Let us draw it here first. 5.72, 70.1 milliamp, and VG is equal to 5.72. So this is roughly equal to supply voltage now. So now that VG is roughly equal to V1, I already recorded my drain current in this table. Now I want to turn my transistor fully on, okay, because I need my load to be equal to my supply. I want all of this 6 volt. So how do we do that? We keep on increasing our gate current beyond this value. So this is 20, so I will just increase it from here. At 7 volt, for example, 7.5, I will just take some random samples. Okay, at 7.5, how much do we get? So this is close to 6 volt, but it's not fully on yet. You still have roughly about 1 volt at your transistor. You want it lower. Okay, so this is 106 milliamp, 106. So 106. Again, I would like to reiterate, the scaling is not accurate. VG is equal to 7.5. Continue to increase. 7, 8. Okay, 8. So it's still not fully on yet. Okay, let me increase this further. 8.8. Okay, 8.8. So 8.8. This is my VG at 8.8. 8.8. So this is my drain current, 123. Okay, 8.8. This is 3. Now if I continue to increase this more and more, at 10 for example, this is 5.96. So 10, this is my drain current will be 134 milliamp. Can you see that the current is already saturating? Okay, at 8.8 we have 1, 2, 3. So at 10 we only have 1 milliamp increase in current. Okay, this is 10.9, roughly 1.1 volt increase. Our current is only increasing by 1 milliamp. So already it is saturating. So I increase this to 13 for example. 13. So this 1 to 5. Okay, it's already saturating. It cannot transcend further. This is what it meant. Increase the voltage until your load voltage is equal to your supply voltage. Right now my load voltage is roughly equal to my supply voltage. So what is the significance of this, you may ask? If you increase your gate current, you will cause more conductivity. If you energize the gate with positive voltage, it will attract electrons here. Okay, but remember, only at specific minimum value of voltage. For example, at VGS threshold minimum is equal to 2 volt, for example, for our specific type of MOSFET, only at 2 volt it is strong enough to attract or to form a channel so that your current can flow. But the channel is very narrow, in a sense. That's why if you keep on increasing your gate voltage positively, there will be more conductivity in your channel, so more current, drain current, can flow, as we witness in the experiment. So the gate voltage determines the conductivity of the channel. So more gate voltage means that more current, drain current can flow. If your VG is equal to your supply voltage, you will only get half of your voltage, as we witnessed earlier here. At VG is equal to 5 volts, our VL is only around 3 point something volt. So at VG equal to 6, which is roughly equal to our supply source, I only get about half or a bit more than half of the voltage across my load. So it means that my transistor is not fully on yet. I still have a large value of voltage here. So in order to turn this fully on, we need a higher gate voltage than our supply. So we have to bias our gate voltage higher than our supply voltage in order to turn our MOSFET fully on, which is at 10 volt. Now right now at 10 volt, which is 4 volt higher than here, only then my MOSFET is in a way fully on. So that concludes our experiment for today.